My dear people, so far we've been looking at the flow of water or any liquid from a higher elevation to a lower elevation. Yeah, but you might be wondering, well, is it possible for us to apply Bernoulli's principle when the flow is happening the other way around? Otherwise, when fluid is flowing or when fluid is pressurized to flow from a lower elevation to a tank or to a section at a higher elevation, is it possible to apply Bernoulli's principle? Yeah, of course, my dear people, of course it's possible for us to apply Bernoulli's principle. Yeah, and let us see how. And that is what we are going to be looking in this particular problem. So what do we have here? Let us just first read this. Okay, a closed water tank is partially filled with water and the airspace above is under pressure. Okay, I have a tank here of section A, and it is partially filled with water and the air above is under pressure. Otherwise, it's applying some pressure on the surface of the water. Okay, a hose of 5 centimeter diameter is connected to the tank. Okay, a hose of 5 centimeter is connected and it discharges water uh, to the atmosphere onto the roof of a building that is 3 meter above the water level. So if this water level is taken as the datum is 0. So if ZA is taken to be 0, then the water is being discharged on the roof at an elevation of 3 meter. It can be the roof of a house, roof of a building, roof of an industry. It doesn't really matter. Yeah. If the total frictional losses are 1.5 meter of water, because the water is flowing up, there are also a couple of bend, which means that water will hit over here and then go over, and it's acting against gravity, so it's going to lose some head. Yeah, again it's hitting over here, etc. So it is totally losing 1.5 meter of water. Otherwise, that is the head loss. Yeah. So they are asking us, what is the air pressure that must be maintained in the tank? So otherwise, what should be PA for it to deliver 15 liters per second of water on the roof? Okay. So the volumetric flow rate should be 15 liters of water per second. Well, we've got to convert it into meters cube per second. Yeah. So that is the discharge that should be maintained. And for that particular discharge to be maintained, what should be the pressure in this tank? That is what they are asking. And that is what I've drawn over here. Okay. So let's look at this problem. I've just highlighted all the important bits for you all so that you do not lose any information. I've just redrawn the diagram here so that it's easy for us, yeah, to see. So what do we know? We have to find the volumetric flow rate in B in meters cube per second, okay, and we have to find what is the pressure in section A. In order to find that, we can apply Bernoulli's equation between section A and section B. Yeah, okay, and also we know that the water is being discharged into the atmosphere, so it is atmospheric pressure, so the gauge pressure is 0 bar. Yeah, and we also know that this is ZA is the datum, so it is 0 meter. Yeah, and also we know that the velocity with which this water is going to go down, this level of water is going to go down, is going to be very, very small, negligible compared to the velocity with which the water is going to flow through this pipe. So I'm assuming that to be 0 as well. These are some of the assumptions that we are making to simplify Bernoulli's equation. Yeah. So first of all, we have to find the volumetric flow rate in meters cube per second. You all know we have, this is the fourth problem that we are looking. In order to convert liters per second into meters cube per second, we just divide it by 1,000. So I get the volumetric flow rate. And in order to find the velocity at section B, all that I'm doing is I'm using the volumetric flow rate equation. V dot B equals AB, otherwise area of section B, times the velocity at section B. Yeah, so I already know what is the volumetric flow rate from here, and we know the diameter is 5 centimeter. So the area would be pi by 4 d square times CB, velocity at section B. If I rearrange the equation, I get the velocity to be 7.64 meters per second. So otherwise, that is the velocity with which water is flowing out of this particular pipe on the roof of this building into the atmosphere. Okay, now I've just redrawn the diagram here. It should have come in the first section itself. So all that I'm doing is I'm just applying Bernoulli's equation between section A and section B. Yeah, I already told you CA, the velocity at section A is very negligible, so I've cancelled it out and it has become 0. ZA is the datum, so I've taken that as 0. PB is 0 because the gauge pressure is 0, because the water is being discharged into the atmosphere. So now everything becomes simple. Oh, what is HL, my dear people? What is it? Huh? Do you remember what is HL? The head loss. The head loss of 1.5 meter that's happening because the water is acting against gravity. Yeah, so there's a loss of head. That is what I've added in over here. Yeah. So the only unknown for me here is PA, the pressure at section A. We know rho, we know G, we know the velocity at B, we know gravity, we know ZB, we also know the head loss. All that I'm doing is I'm just substituting the known values and rearranging the equation, and I'm finding out PA. It comes to be 73.2 kilopascal. Yeah, so the pressure that should be applied in the tank, yeah, is 73.2 kilopascal for the water to be discharged over the roof into the atmosphere, which is 3 meters above the datum point. Do you see? Yeah, it is very simple. Look here, you might be thinking, oh, Venkat has put a lot of calculations in one page, but it's really simple. Yeah, just substitution and rearranging of numbers. If you want, just pause it and then try to work it out on your own and then try to see how I've done it. Yeah, okay, fantastic.